This is 6.2.1, thermal energy transfer. And I'm going to start off by defining internal energy, which is a term you might have come across in GCSEs, but other than just a term, it wasn't really used much. So internal energy is the sum of all randomly distributed kinetic energies and potential energies in a system and with that we have a formula that describes the change of the internal energy. So the change of internal energy is given by delta U equals to Q minus W and here we have to be very careful in how we word things because the wording will change this equation completely. So delta U is the change in internal energy measured in joules. Q, this is the heat that's added to the system. Measured in joules. Now this is quite important because heat can be added to a system, but heat can also be removed from a system. So if heat is removed from a system, then Q will be negative. And so what I will do is I will just double underline this word to emphasize where the heat is going. And then W is the work that's done by the system. So system can sometimes do work, and if it does work, it means it's using the energy that it had and giving it to something else. So W is the work done by the system. And I'll double underline that word by. So the system can do work, but also work externally can be done onto the system. So if work is done onto the system, that W becomes positive rather than negative. So if work is done by the system, W is negative. If work is done on system, W is positive. So that means delta U equals to Q plus W. Yeah? So next, we're going to look at how solids are modeled. So solids, typically, their molecules don't have translational kinetic energies because they don't move around, they vibrate about fixed positions. So they have vibrational kinetic energies. So molecules in solids do not move around, and I'll put in bracket translate. So do not have translational EK. They have vibrational kinetic energies. So vibrational EK. And the way that these are modeled, if we draw some molecules within a solid, it's as if every one of these particles is connected to the adjacent particles with springs. So they behave like they're connected with springs. So just like if you were to imagine springs oscillating, if you were to have more energy in there, then the amplitude of those oscillations will increase. So if we heat up the system, then these molecules or these particles begin to vibrate with larger amplitudes, and so that causes the solid to expand. And if you continue to heat it up more and more, at some point those springs break. So when the springs break, we say that the intermolecular forces have broken down, and your solid then becomes a liquid. So if we heat it, the amplitude of vibrations increases, and if we continue to heat it, bonds will break. So until bonds break, so the amplitude increases, but the period doesn't change of oscillations. Because if we look at the formula for period, it's T equals to 2 pi root m over k. So nowhere does that equation depend on the energy that you put in. Then liquids, because the molecules in liquids can move around, they now have translational EK, plus they have vibrational EK because they can also vibrate. But they can have some rotational EK as well. But mainly it's going to be translational and vibrational. So liquids have translational EK, and I put in brackets, molecules can flow. And vibrational plus rotational. Now for rotational to be able to happen, we're assuming we've got polyatomic molecules. So for example, water, H2O, it's got 3 atoms in there to make one molecule. If it's monatomic, then monatomic can't have rotational kinetic energies. And then finally, we've got gases. So it's mostly translational. And for polyatomic molecules, vibrational and rotational EK as well. So for example, if we draw a simple diagram, so here's a molecule with 3 atoms in it. Because we modeled them as 3 atoms being connected via springs, therefore there's going to be some vibrational kinetic energies in there. And if we imagine this whole thing to live on a set of axes, then the whole molecule can rotate about those axes in any direction. Right, let's start a new page. The new title here is specific heat capacity. Which is something that you actually do at GCSE. But we're going to also talk about non-specific heat capacity, so just heat capacity, because that's not really something that's touched upon that much. So let's say we have some material. For example, an aluminium block. And we place inside this block a heating element. And that heating element is connected to a circuit that can supply it with some energy. And we have some method of measuring the voltage and the current. If we wanted to, we can also make this a variable. So if we simply place a variable resistor here, then we can adjust the potential difference that reaches that heating element. So, some energy is supplied electrically to that circuit. The heating element then converts that electrical energy into heat. So we say energy is transferred to heat. So E by the circuit is equal to Q. And we know from there that E is equal to ITV from electricity. So by using ITV, we can calculate how much energy has actually transferred into the heat. Now, that energy that's turned into heat doesn't all actually go into the aluminium block. So we have some amount of energy in, some of it goes into heating the block, some of it is lost to the environment, to the air in the environment. So we've got energy in, we've got heat into aluminium, and this heats the room or surroundings, which is a loss. Now, as that block heats up, so in the beginning when the block is cold, it's at room temperature, most of the energy goes into the block to raise its temperature and heat it up, and some energy dissipates into the air. But as we make the block hotter and hotter, it starts to dissipate that energy at a much higher rate, until eventually we reach a temperature where all the energy that's going into the heating element is coming straight back out to heat the room. And at that point, the block stops raising in temperature, unless we obviously crank up the voltage of our heating element or get a larger heating element that can do more work per second, so it has a higher power. So at room temp, or ambient temp, this is also called ambient temperature, if we draw our block and we do energy in and we do a small energy out, then as the temperature gets higher, so at a higher temp, if we've got our block, we've got the same amount of energy coming in because it's heating at constant power. We've got constant potential difference and constant current in our circuit, but our energy out now gets a bit larger. And then finally, all energy into the system is equal to all energy out of the system. So all heat in equals to all heat out. So block remains at constant temperature. And that happens when it's hot. Let's start a new page. We'll move on to heat equations. So the first one is just a reminder of the specific heat capacity equation from GCSEs. So we've got Q equals to mc delta T. Where Q is the heat measured in joules. Now, you can get a negative value for heat. If you get a negative value for heat, it means the system is losing heat. It's giving heat to something else. So that when that happens, the temperature goes down. Or you're losing matter. M is the mass measured in kilograms. C is a specific heat capacity. And the units for this are going to change from what they were at GCSEs. So now, the units are joules per kilogram per Kelvin. Because temperature is now measured in Kelvin, not in degrees C. And delta T is the change in temperature. Which is measured in Kelvin. So, reminder, because we haven't talked about the word specific since year 1, the word specific in physics means per unit mass, like specific charge. So, specific heat capacity is the heat capacity per unit mass. And I like to use the analogy of thinking about a kettle that's full of water and a swimming pool that's full of water. It will take much more energy to raise the temperature of a swimming pool full of water than it would to raise the temperature of a kettle full of water. However, once you've divided by the mass, they both have the same specific heat capacity. So by dividing by the mass or finding per unit mass, you've now taken what a single situation's property is and turned it into the material property. So water has a particular specific heat capacity, but a swimming pool has a larger heat capacity, a non-specific heat capacity, than a kettle full of water, because it has a much larger mass of water. So heat capacity, and I'll put in brackets here, non-specific, is joules, measured in joules per Kelvin. And I'll stress here as well, because this might be the first time you're actually using Kelvin, some people default to saying degrees Kelvin. We don't say the word degrees when we say Kelvin, it's just Kelvin. Belongs to the object. So for the same material, the more massive has a larger heat capacity. So this has a heat capacity which is big, and this one has a heat capacity which is small. But because they're the same material, they have the same specific heat capacity. So we use a specific heat capacity equation when there is a change of temperature. So where we add heat into a system or take heat out of a system and its temperature changes. But other than temperature, we can also change the state of a material. And during a change of state, the temperature ceases to change until all of that material has changed state. Then would the change of temperature resume again, assuming that you're constantly adding heat in. So this whole time we're constantly adding heat in. So for a change of state, we use a specific latent heat of fusion or vaporization. So Q equals to mL. Put a box around that. Again, Q is the heat, so I'm not going to write that down. M is the mass, but L here is the specific latent heat of fusion or vaporization, and it's measured in joules per kilogram. So now we've just got two words to contend with, fusion and vaporization. So fusion is between solids and liquids, or the reverse. And vaporization is from liquid to gas, or the reverse. So for each material, say water, H2O, the specific latent heat of vaporization and specific latent heat of fusion will be two different numbers. So you have to pay attention, especially in a multi-step process, what's happening in each process. Start a new page. So lastly, it's heating graphs and definitions. So we'll do time on the x-axis, measured in seconds, and we'll do temperature, measured in Kelvin, on the y-axis. We will start at a non-zero value at t equals to 0. So at time equals 0, we have a non-zero value of temperature, because if it were 0, that means it's absolute 0, which means we don't have anything that's minus 200 and whatever. So we start from a non-zero value, and we go up in a straight line. So at this point, we are heating the system and its temperature is rising. So if we started with a solid, then here we've got mc delta T. It's raising in temperature. Then it reaches a point where its temperature remains constant. Now, if we're supplying energy at constant rate here, then that means this here is the melting point. So that's melting. Melting point. So here we've got M, L, but it's not ML vaporization, it's ML for fusion. So ML, and I'll write in subscript, fusion. Then, once it's all turned into liquid, the temperature can rise again. So this again is mc delta T. But here it's the C for the solid, and here it's C for the liquid, which can be different. Then it remains constant again for a while. This is the boiling point. And here you got ml vaporization. And after a little while, once it's all evaporated and turned to gas, then can the temperature continue to rise. And then we've got MC delta T again here. But this time it's MC gas delta T. Now, depending on the direction that you're moving in on this graph, it can be melting or it can be freezing. So as time goes forward, if the temperature is dropping, then you know that you're going to have something that's going from a gas to a liquid or a liquid to a solid. If the temperature is increasing as you have those plateaus, then it's going the other way. It's going from a solid to a liquid, then liquid to a gas, because it takes higher temperatures to change to those states, not lower temperatures. So here, let's do assuming heat is supplied at constant rate. And that basically means that power is constant. Now, let's add definitions. Specific heat capacity. Is the heat required per unit mass of a material to raise its temperature by 1 Kelvin. Then for specific latent heat, this is the heat required per unit mass of a material to completely change its state without a change in temperature. And that's the end of 6.2.1.